Okay, so a flea with mass 0.58 milligrams jumps directly vertically, reaching a height of 29 centimeters. How much work in microjoules do the flea's legs do to accelerate the flea? All right, so the way we're going to think about this is that the initial energy of the flea is zero, right? It's just sitting on the ground. It has zero potential energy. It's got zero kinetic energy. It jumps up, so now it has potential energy, and the height is 0.29 meters, which is 29 centimeters. Okay. So where did it had zero energy to start, and then at the end of this jump, at the top, it's got a bunch of potential energy. So where did that energy come from? It came from the work done by the flea's legs, right? So it was zero energy. The flea's legs did a bunch of work. Remember, work is a transfer of energy. And that's where it got the PE from. So PE is equal to mgh. And we're almost there already. The mass is going to be a little bit harder to get just because it gives you in 0.58 milligrams. And so if you think about the conversion, what you got to do here is there's 1,000 milligrams in a gram, and there's 1,000 grams in a kilogram. Remember that in order for these formulas to work, the mass has to be in kilograms. So really what you're looking at here is it's going to be 5.8 times 10 to the negative 7th kilograms when you solve it all out. So that's going to be your mass. The g is going to be 9.81 meters per second squared, and the h is going to be 0.29. So the way this works, again, is that the potential energy at the top of the jump is now 5.8 times 10 to the negative 7th times 9.81 meters per second squared. I always leave the units out when I do calculations because it just clutters up my equation. The height here is 0.29 meters. And if you plug all that in, you're going to get, let me just bring it down here. You're going to get that the PE is equal to 1.65 times 10 to the negative 6 joules. However, it wants it in microjoules. A micro means 10 to the negative 6th, right? That's what micro means, 1/1,000,000th of something. So notice that this is already at 10 to the negative 6, so this is going to be 1.65 microjoules. And I mean, I guess technically if you want sig figs, we have 2 sig figs here, and so, it's possible that he might want the answer as 1.7 microjoules, but I'm just going to leave it as 1.65. Okay, so an ice boat is sliding across a frozen lake with wind blowing at an angle of 27.3 degrees relative to the direction of motion. The wind apply a force of 395.76 newtons. How much work in kilojoules is done if the boat travels 100 meters? Okie dokie. So in this case now, let's just pick a direction. I'm just going to pick to the right here. And I'll make this a little, actually, I think I might make this a little bit bigger. So we have the boat traveling this way, however the wind is coming in like this, and so this theta right here is going to be 27.3 degrees. The force of this force vector, the wind, is going to be 395.76 newtons. This distance that it's been traveling is 100 meters. All right, the wind has been going this entire time, like that. And we're trying to figure out how much work in kilojoules. So the first thing we got to think about is work is equal to FD. Well, the D is easy, 100. However, the force, we got to be a little careful. This boat is traveling in the X direction in my picture here. So this force right here, notice that it's not in the X direction, it's at an angle. So not all of this force is going to do work on the boat. It's the component of the force that is parallel to the motion. So let me just redraw this for a second. If the force goes at an angle, that means that there's some of the force directed upwards. We'll just call that Fy. And some of the force is directed in the X direction. We'll call that Fx. Only the Fx is actually in line or parallel to the motion of the boat. So it's really only the Fx component that can do work on this boat. So it's not just simply a F times D situation. We got to figure out what the Fx is and then times the D. So let's go back to go back to red. So if we look at this triangle right here, the sine, I'll just do this part in blue. Notice that if this is the angle right here, we're looking for the adjacent side. That's fx. So remember, SOHCAHTOA. That means that we're going to be using the sine or the cosine function because we're looking at the adjacent side. So let's think of it for a second. The cosine of theta, remember theta is 27.3. That's equal to the adjacent over the hypotenuse. And the hypotenuse is the actual full force vector, which is 395.76. So if you want fx, if you want that x component, you got to go 395.76 times cos 27.3. That's going to be your fx. So now jump back up to here. Work is 395.76 cos 27.3 times d, and our d is just 100. So now if you plug this in, I'm trying to find out what my calculation was. There it is. If you plug this in, the calculator is going to give you an answer that's going to say like 35,167.9 joules. It's asking for it though in kilojoules. And so here again, if you care about sig figs, there's 3 sig figs in that 27.3. So let's just go to 3 sig figs. Although I guess technically there's just 1 right there. So what I'm going to do is I'm just going to round. I'm going to use reasonable precision on my answer without being so technical with sig figs. Your prof might want sig figs. I'm going to use reasonable precision. This is 35.2 kilojoules, right? 35,000. There's 1,000 joules in a kilojoule. So this is about 35.2 kilojoules. And again, if we were to go strictly by sig figs, there's only 1 sig fig in 100. I don't feel like rounding this to 40, so that's why I'm going to leave it as 35.2. So here we have a spring with a spring constant of 5.1 newtons per meter, and it's compressed by a total of distance of 7.4 centimeters. How much work in millijoules was required? So in this case, I just there's my page. We need the formula for the work done by a spring. The work done by a spring is equal to 1/2 kx squared. And really briefly, if you don't know where that comes from, if you think of a force displacement graph of a spring, the greater the force that you apply to a spring, the more it stretches out. And so since work is equal to FD, it's really just the area under this line right here. And since F is equal to F is equal to mg, and long story short is the area under this curve is the 1/2 kx squared. Okay, let's just leave it like that. I'm not sure if you needed to know that or if you're just given the formula, but that's where this formula comes from. If you're already given the formula, then just don't worry about it. So the work done by a spring, 1/2 kx squared. And remember that k value of a spring is kind of like a measure of how stiff the spring is, right? A big k value means that it's really hard to compress the spring. It takes a lot of force to compress it. And a low k value means it's like a floppy, sloppy spring that's just super easy to compress, and it doesn't give much resistance force at all. Well, anyways, they give you the k and they give you the x, which means this is a straight plug and chug question. You got 1/2 k, and that k value is given as 5.1. The x value is given as 0.0474 because it's 7.4 centimeters, and we're going to square that. So the calculator will tell you that that's 0.013968 joules, but remember they want millijoules, and which means thousandth of a joule. There's a thousandths place right there. So this is going to be 13.96 millijoules. Or most likely what they're looking for is 14 millijoules. If you go by sig figs, 14 millijoules. Alrighty, you gotta love multiple choice questions because even if you have no idea what you're doing, you got a chance. You're telling me there's a chance. A heavy badger and a light gopher are balanced in a massless seesaw. So here's the seesaw. Now it says heavy badger and a light gopher, so I'm just going to call the badger B. Now if it's heavy, that means that it's probably closer to the axis of rotation, or the fulcrum if you want to use a vocab word and impress somebody. You'd go ahead and do it. That's my badger. And if it's a gopher, it's a light gopher, it's going to be somewhere out here. Just arbitrarily, it's going to be further out. G. I just want to point out that you know that the badger is closer because of this idea that torque is equal to F times R. R would be a distance away from the pivot point. And so if you know that the badger has a heavier mass or heavier weight going down this way, which is mg, then if the badger has a higher F value, then it better have a shorter R value if the torque is going to equal the gopher's torque. Let me just be a little bit more obvious about what I'm saying. The badger is going to exert a torque going this way, right? Because it's on this side and it's pointing downward. So there's a torque in the, clockwise direction. The badger would be counterclockwise. The gopher has a weight going down this way, so it introduces a torque in the other direction, so the gopher would be introducing a torque in the clockwise direction, right? So just that would be going this way. This one wants to make it go this way. So that's what I mean. And since torque is equal to the force applied times the radial distance away, the badger has a higher force because higher mass. I'm taking a lot of time to explain something that you probably just know intuitively, which is if they're going to be balanced, the heavier object has to be closer to the fulcrum. That's all I'm trying to say, but I'm just telling you the physics of why that is. All right, so let's get down to the nitty-gritty here. The torque that the badger produces is equal to the force of the badger downward times the radial distance away of the badger. Let's just call this R sub B. The radial distance away of the badger, R sub B. You know that the torque that the gopher produces is going to be the force of the gopher's weight times the radial distance away of the gopher. So we'll call this R sub G. These two forces have to be equal because that's what the problem says, it's balanced. All right, so you know that these things have to be equal. So the torque of, this is how we're going to write it. Okay, now I'm going to zoom in here for a second. The question says if they both move forward so that they're 1/3 their original distances. So let's just imagine what's happening here. That this badger has now moved in to this position here. All right, that's the new position. Let's say that the gopher now has moved in, so it's only 1/3, which is going to be this position here. Which means that this new distance R is only going to be 1/3 what it originally was. And this distance right here is only going to be 1/3 what it originally was. And we're trying to figure out if this upsets the system, right? So we're going to put this into our formula. We're going to compare. Well, let's just put it in here, and I'm going to put it in blue. Now, the force of the badger has not changed. The badger's mass is still the same, right? mg, the weight is still the same. However, we now have 1/3 the original. I guess not a capital. I shouldn't switch. We have 1/3 the original distance away. The force of the gopher has not changed, and it is now 1/3 the radial distance away from that it originally was. Okay, so I want to point out something, that everything is the same. Where we haven't changed the force, the weights. We haven't changed what the original radial distances away, the radius away, are. All we've done is introduce 1/3 factor on both sides. If you multiply 1/3 on both sides, you have not changed one bit the relationship between these two sides. Another way of saying that is, if this is equal right here and it balances, if you multiply both sides by 1/3, it still balances. They're still the same value. So the seesaw is going to remain balanced. That is a long way of explaining in physics something that most people probably intuitively know, that if they both go in by the same proportion, if they both go in by a third, they're going to stay balanced. And that's how you do that one.